Hello everyone, welcome to GATE Pass. So this is the second part of solving problems on thermodynamics which appeared in GATE 2022. We are going to solve first problem 37. Okay, in this problem it contains a combination of two processes. One is your constant volume process, the other one is constant pressure process, and they have asked you to find out what is the total heat transfer for the combination of these two processes. So as usual, what we will do is first we will study a little about the concept which we will be using for solving this problem. Okay, so what we will be using is the definition of CP and CV. Okay, so what are CP and CV? These are heat capacities. Historically, they used to define heat capacity as dQ by dt. Okay, this was way back in history when thermodynamics was being developed. At that time, people used to think that heat is some kind of liquid. So the substance which is at a higher temperature, it has more of that liquid, which they called heat. Okay, and and when it was brought in contact with a substance which is at a lower temperature, then this liquid they thought was transferred from a higher temperature to a lower temperature. Okay, so at that time this definition came into existence, and that's why we call it heat capacity, because it gives you an idea of how much heat a substance can hold. Okay, so that's why we still call it heat capacity. So it was initially defined as how much amount of heat you have to transfer to a substance in order to bring about a 1 degree change in the temperature. Okay, so but the problem with this definition of heat capacity is that it makes it path dependent, because the Q which you are using over here is a path function. Okay, so two definitions of heat capacities were given so as to relate it to some state function, so that these values also become state functions. Okay, so the first one which was given is Cp. It is defined as the partial derivative of U. Oh, I'm sorry. This is Cv. Okay, so Cv is defined as partial derivative of U with respect to T at constant V. Okay, and the other one which was defined was partial derivative of H with respect to T at constant P. Okay, now I can also write this as, so for that I can write as du, it will be equal to Cv integral dt for a closed system. Okay, and which is taking place this for a closed system and a constant volume process. So I can write du is equal to Cv dt. Of course, if Cv is independent of temperature, otherwise I should actually write it inside this integral. Okay, so du is equal to integral of Cv dt for a constant volume process and a closed system. So I am writing this for a closed system and a constant volume process. Okay, now in this problem they have given that Cp and Cv are independent of temperature, so I can take this out of the integral and write it like this. Further, because I have been given 2 points between which I will be integrating, so I can write it in an integral form like this. Okay, so this is one equation which we are going to use. This is for the constant volume process which is taking over here. And the another equation which we will be using will be Cp. Again, let's see, for a constant pressure process which is taking place in a closed system, I can write this as dH, that is equal to integral Cp dt. If Cp is independent of temperature, I can take it out, and if I am integrating between 2 points, known points, then I can write the integral form like this. Okay, so these are the two equations which directly come from the definition of Cp and Cv. Fine. Now you are not asked to calculate delta U and delta H, but you have to find what is Q. So now I am going to relate these two with Q. Okay, so let's do that. I am going to retain these two equations over here. Fine. Now since this is happening in a closed system, okay, further we assume that this is a mechanically reversible process. In that case, your delta U will be given as Q plus W. Because it is a mechanically reversible process, then I will write my work done, that is equal to P delta V. Okay, so for a constant volume process, this is equal to 0. So my delta U is equal to Q, and that is given by CV dt. Okay, or CV delta T. Now let's see this constant pressure process. Okay, in constant pressure process, again delta U is equal to Q minus P delta V. Okay, P is a constant, so I can take inside, I can write delta of PV. Take it on that side, you end up with U plus PV, that is equal to Q, that is nothing but your delta H. So for a constant pressure process, your heat transfer, that is equal to delta H, and delta H you can calculate as Cp delta T. Okay, so these two things which we are going to use. So I will erase everything and just write down the two equations which we have found out. So you have Q for a constant volume process, that is, I will write it QV just to mark that it's for a constant volume process. Okay, that is equal to U for that process, I should say delta U, and that is equal to CV, and let's say what is the temperature over here? It is going from T1 to TA, so I will write down as TA minus T1. Okay, for the next process, that is a constant pressure, so let's write what will be the Q, that is equal to again your delta H, that is equal to Cp, and what is the difference in temperature? That is T2 minus TA. Okay, so you have to just add these two quantities now in order to find out your complete T. So that's what I am going to do, and at the same time I will just open the bracket so that I can solve it. Okay, now TA is common. I don't know what is TA at this point. Okay, I know that this is P2 and V1, point A, but temperature is not known. So I will try to eliminate this TA with some known quantity. Okay, so let's see how I am going to do it. So I have been given Cp minus Cv is equal to Nr. So I will take out the negative sign. Cp minus Cv, it will become TA minus CVT1. Now again I will now replace my Cp from here. So I will write down over here plus Cp is nothing but Cv plus Nr T2. Okay? Now Cp minus Cv is nothing but Nr. So I am going to write Nr Ta, because minus of this, minus Cv T1 plus Cv T2 plus Nr T2. Okay, now at this stage I am going to use, let's first do this. Okay, oh, this is I think Cv. Okay, so first of all I am going to write this Cv T2 minus T1. Now for simplifying these, okay, I am going to use the definition of ideal gas, which is PV is equal to nRT. Okay, so now nRTA is given. TA at that point, what is your P and V? That is P2 V1. Okay, so instead of nRTA I am going to write P2 V1. So it is minus P2 V1. Now let's see nRT2. Okay, so at point 2 nRT2, that will be equal to P2 V2. Okay, P2 V2. So then your final answer becomes P2, that is minus plus, okay, P2 V2 minus V1. Fine. So I have calculated what is the Q which is required. Now let's see which of these options is correct. P2 V2 minus V1 plus Cv T2 minus C1. So your option A is correct. Okay, so this was a very simple problem which required only the definition of Cv and Cp and how it is related to Q for a constant volume and a constant pressure process. Now one thing I would like to tell you over here, which you should always keep in mind, and there has been no problem in GATE regarding this, so it's a matter of time when it appears in GATE. Okay, so for a constant constant volume process, your delta U is equal to CV delta. I should write, now I will write it like this. du is equal to CV dt. Okay, for a constant volume process. But however, if you have a process in which your volume changes but it returns back to the same volume, okay, still you can calculate your change in internal energy using CVDT, but then at that time it will not be equal to the heat transfer. Okay, similarly, if you have dH is equal to CPDT and you are undergoing a process in which your pressure is undergoing a change but it comes back to its original value, still you can calculate your change in enthalpy as CPDT, but at that time it will not be equal to Q. Okay, so they might ask you a question about such a process, and they can ask you what is the change in what is the heat transfer. At that time you can use, okay, calculate du using this and then calculate work, and then from the first law you will have to calculate your heat transfer. Okay, so the second problem which I am going to take is problem number 49, which came for 2 marks. In this you have been given the value of ln of P saturation, so that is the saturation pressure, and against the temperature T in Kelvin. Okay, so you have 2 data points and they have given you the value of R and asked you to calculate the molar latent heat of vaporization. Okay, so in order to calculate that you need Clausius Clayperon equation, which we will be deriving next. Okay, and then applying that equation is a matter of just a couple of minutes, and straightforward in 2 steps it will give you the answer. But let's first go through the concept. Okay, so in last video we had seen that when 2 phases are in equilibrium, then the molar Gibbs free energy, that is the free energy per mole in liquid and vapor phase, are same, and that brings us to even the change in that molar Gibbs free energy, that should also be the same in liquid and vapor phase. Okay, so I am writing dG, that is equal to VdP minus SdT for the liquid phase and for the vapor phase, and I am equating it. Okay, rearranging it, I get this equation. Now I am defining the change in the volume per mole, that's the molar volume, when the phase changes from vapor to liquid phase as delta VLV. Similarly, for the phase change, I am defining my delta SLV as SP minus SL. Okay, so I am putting these variables over here. Now I rearrange this equation, I get dP saturation, that is equal to delta SLV upon delta VLV into dt. Okay, now delta SLV, I don't know how to calculate right now. So what I am going to do is I am going to replace this value. So for that I am going to use this definition. Okay, so GL is equal to GV. So I am writing it as H minus Ts for liquid phase, H minus, that is equal to H minus Ts for vapor phase. Again do the rearrangement, delta HLV and delta SLV means the same, that is the change in the property when the phase changes from liquid to vapor phase. Okay, from that what I get is that delta SLV is equal to delta HLV by T. Okay, so now I am going to put this equation, this quantity in this, and what I get is dP sat, that is equal to delta H LV upon T dt, and that also has delta V LV. Okay, now I have to calculate delta H LV. Further, they have asked you to assume, okay, that your vapor phase is an ideal, is behaving ideally, that's it's an ideal gas, and your liquid phase, the volume is negligible. Okay, so delta V, how we have defined delta V LV, that is defined as V, that is the molar volume of the vapor phase minus molar volume of the liquid phase. They have asked you to take this as negligible. Okay, so then your delta V LV under this assumption becomes equal to the volume of the molar volume of the vapor phase. Now molar volume of the vapor phase, then we know that because they have asked you to take it as ideal gas, so PV is equal to nRT, right? It's molar volume, so I am taking V by N, so that is the molar volume I am taking. Now P is nothing but P sat, so your V becomes equal to, that is your for the vapor phase, so your V becomes equal to RT upon Psat. So let's put this value over here instead of delta V LB. So what I get is delta H LB upon RT Psat dt. That is equal to your dPsat. Okay. I have another t over here, so it will be t square. Fine. Now let's separate the variables. So I have dPsat by Psat, that is equal to delta H LV upon R dt by t square. I will do some mathematical manipulation. Instead of writing it as dPsat by Psat, I can write it as d of ln Psat, and that is equal to dt upon t square. I can write it as minus of d 1 by t. Okay. Now I will take that over here. So this is minus of this thing. So I will have minus d ln P saturation upon, that is the differential of ln of Psat with respect to 1 upon t, that is equal to minus delta H LV by R. Okay, so this is your Clausius Clayperon equation, which you have derived from your Clayperon equation under two assumptions. One assumption is that your vapor phase is behaving like an ideal gas, and your liquid phase, the molar volume of the liquid phase is very small as compared to the molar volume of the vapor phase. Okay, so this is the equation which we are going to use. Now you will see how quickly the answer comes. We have to find out delta H LV. So I am going to write this equation: d ln of P saturation by d of 1 by t, that is equal to minus delta H LV by R. Okay, so delta H LV, that is the molar latent heat of vaporization, that is equal to R times. Now since 2 points have been given, so I will just use it in an integrated form, and I will write ln of let's say P2 sat minus ln of P1 sat upon 1 upon T2 minus 1 upon T1. Okay, so, and of course you have to retain your minus sign. So minus delta H LV, that is equal to minus R. What is P2? 1.386, that is ln, so I can write it as 1.386 divided by 0.693. Okay, this comes out to be ln of 2. So again ln of 2 is 0.693. So this is basically this value is 0.693 multiplied by R, and in the denominator you have 1 upon 370 minus 1 upon 350. Okay, so it's a very simple mathematics. You can do it. Put the value of R as 8.314. So the answer which you will get will be in joules per mole per Kelvin. Okay, but they have asked you to calculate in kilojoules. Okay, so what I will do is I will divide this further by 1000 so that your answer directly comes in kilojoules, and your answer comes out to be 37.3 kilojoules per mole. Okay, so just keep in mind that the units of heat of vaporization, it is kilojoules per mole. The Kelvin should not be here, so I just made a mistake, so I am correcting it right now. So it's the units are kilojoules per mole. So once you know this equation, that is the Clausius Clayperon equation, you can solve it within 1 minute. So it's a 2-point question, and you can solve it if you remember your Clausius Clayperon equation. So I hope you liked the video. If you like the video, please don't forget to subscribe and like this video and subscribe my channel. And if you have any question related to thermodynamics, please leave it in the comment section and I will try to answer it. So thanks for watching. Thank you very much.